Hello, everybody. This is Kei May Lau from the Hong Kong University of Science and Technology. I'm going to talk about this topic, electronic-photonic integration, EPI, and or you can call it EPI, because I do EPI, and then with cross-generation semiconductor technologies. And then, so I'm going to share with you the basics of different generations that people are talking about, and I will also showcase this integration of technology that we have been doing at the Hong Kong University of Science Technology, and how do we use this electronic and photonic integration for these purposes. So exactly what are the different generations? And the first generation, of course, everybody knows is silicon. And silicon is being used at probably 95% of the market, of the semiconductor market. And the second generation, and the people may call it's a gallium arsenide, indium phosphide, and the alloys of the 3,5 alloys. And these compound semiconductors have also been used for a long time, and particularly for microwave integrated circuits and monolithic integration and the photonic devices, and it's for the lasers, the communication, fiber communication. And since the 60s and 70s, I would say, for microwave devices, it will be discrete devices in the 60s. And then for the photonic devices, probably in the 70s. And then from then on, it's this always been used all this time. And then the third generation semiconductor, and it's a more recent, and I try to emphasize it, and these are the commercial wide bandgap semiconductor, and these are the wide bandgap semiconductors, and it's a gallium nitride, silicon carbide, and these are the crystal structure of gallium nitride and silicon carbide. And as you can see here, these wide bandgap is over 3 electron volt, and there are also other compounds that are also wide bandgap. And then I said it's a commercialized wide bandgap semiconductors, and these are the materials that the industry are using to make devices. And of course, for the lighting and display applications for gallium nitride, and also this for the electronic applications. And you can see here, and for the frequency band and the power applications. And gallium nitride is the one material that can get to high frequencies, and also that can make power devices. For silicon carbide Mosfet, it has been developed for a long time, but it's mainly for the power applications, but not being able to get high in frequency. So it's you can see here this beyond the 3 gigahertz, and gallium nitride, it's essentially the one materials that can cover both the high frequency and high power. For gallium arsenide or indium phosphide, it can get to very high frequency, but the power, yes, the power handling capability, it can be better than silicon, but it's not as high as the gallium nitride. So I also kind of the people call this different generations, and I want to make it clear, and that this people might have the misconception. Okay, generation 2 is out, then it's we can get rid of generation 1, and 3 is out, we can get rid of generation 2. It's like all the other stuff, the newer generation, that means it's replacing the older generation. And what I want to emphasize, it's not true. It's each of the generation and has their specific applications. And that's why my talk is about using and combining the different generation, and so that we can do more, and we can do more integration, we can add more functionality, and so on. So first of all, I will talk about this gallium nitride, and now it has been developed for power applications for the past 15, 20 years, and people are calling it, it can like break the limit of the silicon power devices. And what is showing here is people have been doing comparison, and for the silicon based and this inverter, and it used to be like this size, as you use gallium nitride, and you can get down to the size of a sticker note, and this is a 2 kilowatt. And these might be for people that are more specific, using this power inverters, but then for everyday people, and you can see that your laptop and used to carry a 60-watt charger, and it's like this, and it's very heavy, and like you carry around a brick. But now you can replace it with this little thing that you can put between your fingers, and it has a 60 watt, and you can charge up your laptop and your mobile phone. And well, no one carry a digital camera these days, and you can charge up your camera and whatever that you have. So this is for the consumer electronics. And gallium nitride, it can make all these components in the consumer electronics. And then the main advantage, as you can see here, you can downsize, and it's a much more compact, and it's because it's a small, you use less material, so it's a cost effective, and because you can switch it much faster in the whole system, and because you can use a smaller passive components, so that less parasitics. And then these devices, the arm resistance, and you can make them very low, and we can show it some later on. So it can, it's more efficient, it's cooler, and then there's a lower loss. And also it can stand a very high temperature. So you can get to more applications in addition to the consumer electronics. You can get to the automobile, and you can get to this renewable energy and others. And you can see here, this is the voltage that these devices can get to, and in up to a couple thousand volts. And so these are the comparison. On the left-hand side is the comparison of gallium nitride, silicon carbide, and silicon. And in this different aspects, in the high temperature aspect, in the high frequency aspect, and also in the high voltage aspect. And this you can see it, the silicon carbide is definitely this high voltage and high temperature. But for high frequency, and it's definitely gallium nitride is the one that is winning out. And this orange is this little thing. It's for the silicon devices. And so another thing that I would talk about later on is the optoelectronic material and devices that are combining the generation 1 and generation 2 semiconductors. That means it's silicon. And for those of you who are working on photonics, and the silicon photonics has been being developed for the past 20 years, and it's really fast, and people are really deploying the silicon photonics. And so these are the photonic integrated circuits for data communications in all the data centers. There's a huge need for that. And then people have been using compound active devices, like laser photodetectors and modulators and so on. And we try to integrate these devices and for the optical interconnects, because these the compounds are more efficient devices, and you can have a higher speed. And the silicon photonics, the whole purpose of integration is for high speed, is for lower power consumption, is for a larger bandwidth, and also a lower latency. And so you can see people have been doing that, integrating silicon CMOS and silicon waveguides, and for the on-chip optical interconnects. And these is showing the different components, the photonic components, and people are trying to integrate on silicon. And these are a couple of the examples that we have been working on. It's 3.5 laser arrays. And you can see the size of these laser arrays. It's just a few tens of microns. And then these the width, it's a few 100 nanometers. And we are doing investigation on this small 3.5 laser arrays that is being put on SOI. So these are the telecom 3.5 lasers that can be grown directly on SOI. And I'm going to talk about that later on. And let's just switch gear. Is another, this is a 3rd generation semiconductor that I want to tell you more about. It's you probably heard about this, is the micro LED. There's a gallium nitride based micro LED, and people are trying to make this a huge wall and this huge screen, and also the Apple have been announcing they're going to put micro LED on the Apple Watch, and people have been doing that by different approaches. And this is one of the topics that we have been working on. And so this, for the next generation display, you can use the conventional LCD. There are like many layers, and the brightness is low, and also the contrast ratio is low. And for the organic LED, you can improve that somewhat. And then, but then there's still challenges in the lifetime, and also the brightness of the blue organic materials, and this is the challenges, and people are still working on. For the micro LED, which is based on the gallium nitride LED, also these the red color, it can be made with the very mature atom gap. And these are inorganic LED. It has a very high stability, and the lifetime is long. And then you can make it very bright and very visible under the sunlight. And then this is the ultimate solution. And in my opinion, it's for the AR, particularly VR and AR, particularly the AR, because you really need the brightness for AR. And so this micro LED, where is this position? And so for very far away, larger screen, and you don't you need this pixel per inch is around 60, and around 0 to 1 pixel per inch. And then this view distance is 10 meter. Or if you can direct view TV and phone, you can use the LCD, mini LED, and plus the LCD. So these you can solve this with the conventional technology, but for micro LED, and you need the high resolution, and it's 1,000 PPI, and this for AR and portable projectors and VR. So these we believe is people are using LCOS, LCD on silicon for some of this solution, because the other technology are not good enough and not like mature. And so this micro LED is the ultimate solution for AR and portable projectors, and because it's the high brightness that is needed. And so this is a market gap that people are trying to fill. So this is the micro LED. high brightness, high resolution, and this is what people are working on. And these are the worldwide developments of this micro LED technology. And most of people are using this pick and place and trying to put this the small individual pixels, and then do the pixel transfer. People call it transfer printing or mass transfer. And these, it makes sense if you are working with a larger pixel size, and also the pitch, the pixel pitch is large. And the other approach is a monolithic approach, and this is what we have been working on. And this is a 400 by 240 micro LED micro display. It's all monolithic. And this is what we have been made about 7-8 years ago. And this is by using a single nitride chip and do all the fabrication. And then after the fabrication, you do the bonding. And so this is for the small pixel pitch. It can down to a few micron pixel pitch. But then it have the difficulty to make the full color. And we recently find a solution for that. We are not 100% sure that's the ultimate solution, but it's right now it's pretty good. This is adopted by a few companies. The bigger ones are Sharp, Prezi, and the startups, the JBD and Raysoft. And so this why is a monolithic approach, and combining as a generation 1, this is silicon and gallium nitride, and we made this LED on silicon chip. And this we chose this monolithic approach because you don't have to deal with this micron size pixel, that millions and millions of them to handle and to do the pick and place or mass transfer, whatever. And then there's an integrated circuits technology that you can use, and in the clean room. So the technologies is there. You just apply them to make this monolithic LED chips. And then what you align, the alignment is between your LED array and your CMOS driver chip, or you can use a TFT. And then you can customize the chip size, you can customize your display size, and you can do module tiling, just like the big TV, the big companies are doing. And unfortunately, and it is monochromatic in nature. So, and depending on what you are starting from, the color of your compound semiconductor. So this is I can quickly go through that, how we make the LED array, and then with combined with the CMOS driver. And then this LED array is grown on the silicon. It's a blue LED array grown on silicon. And then you can process it into whatever pixel size that you like. And then you do selective electroplating for the bonding. And then after that, you do the bonding on a CMOS driver. And then you can remove this silicon substrate and that was grown on, and you can do a dry etching or combine dry etching and wet etching. This is the Cmos Backplane that we have designed for various displays, and this can be done in the foundry, and we did this and combining with the other functions, and because I was working with some colleagues, and they want to include this visible light communication on this display technology. So this is showing you some of the driver design that we have made, and using this copper tin bonding with the micro LED array. So this is the recent development that we have gone from There's a monochromatic, the blue and the green, and to there's a more recent, the full color display. And this is the high resolution full color 423 PPI that we made. And this is we use this quantum dot photoresist technology, and with the flip chip bonding, and we were able to make this full color display. And this is can be for the AR and VR applications. And you can see that this RGB is pretty good. So switch gear again and go to this power devices I was talking about earlier. And then this is a power device that we have been working on recently. And this is a vertical device. And this you can see we have been working on lateral device for a long time. And typically they are normally on. And also, and this lateral device, if you want a high power, then you need to make a lot of fingers, and then your footprint is quite large. And then meanwhile, and we know that people in the silicon and silicon carbide, and they have been making the trench device, and these can be very high power, and then you do not increase the footprint very much. So we want to apply this similar technology and using the vertical gallium nitride trench MOSFET. And then these, this is a comparison of people have do some preliminary studies, and I think it was an MIT group. And then we find that this advantage of the vertical design, and it's a high current density, and you can if you look at the silicon or silicon carbide, it can really handle very high current density. And with the gallium nitride, it's even higher. And also extremely high voltage. And then it can be a better thermal performance. And also, it's very important because most of the lateral devices normally on. And these are the normally off device. And these vertical can be easily made normally off device. So this is insulated gate, MOSFET, and the epitaxy structure is an NPN epitaxy structure. So the MOS gate is it's very effective in blocking the gate leakage, and then you can make the submicron channel length because the channel length is in the P channel, so it's determined by the thickness of your P layer. And then it can, the PN junction, because the PN junction, it can have the avalanche breakdown capability. And then the source drain channel doping, it's again, it's controlled by epitaxy. So we don't need to use any implantation. And we actually did a doping study of the body channel, and we find that we can control the drain current in a very large extent. And then you can grow this on silicon carbide, you can grow this on sapphire, you can grow this on silicon substrate. So there we did some preliminary investigation of the P body, and then the oxide channel interface, and also the drift layer thickness, and we also study. So again, this is the combination of generation 1 and generation 3, the vertical trench power devices. And we did this in our MOCVD systems, and we can grow crack-free gallium nitride on silicon. And we make these trenches. And then these, we originally that we tried this concept. We had this proof of concept that have this grown on sapphire, because in this case we can grow this the N- layer thicker. So this we have proved that it has a very high drain current, and the on resistance was very low. And then we also put it on the silicon substrate. So this was the p-body doping study we did on sapphire. And what we find is that we change the p-body doping, and not that much. It's all in the 10 to the 19 range. And this is the magnesium concentration. Of course, the whole concentration is somewhat different. It depends on your activation efficiency. So what we found that the drain current, that is the 5 samples that we have, and that's a huge difference. And also the threshold voltage. And then you will have to choose whether you want a high threshold voltage or the high ID max. And then we show this in our recent publication, and the relationship and how you can optimize according to your design and for the threshold voltage and the drain current that you would like to use. And also, we also developed this vertical trench technology by filling this the bottom of the trench with the EOC, and we can improve the breakdown of this transistor with the thick bottom trench and to up to 525 volt. And so we have do a benchmarking of these devices and compare with our device in terms of the RR, the low RR, and then the breakdown voltage. It is comparable with the devices that are on silicon carbide, and then it's the best among those that are on silicon. And so we think that this technology is a very promising. And so this the figure of merit and the political figure of merit is very high. And so we will continue to pursue this technology on the different substrates. Okay, so this is showing you that we also tried this technology on a silicon substrate in a preliminary study and find that this ID on is even higher. It's really amazing. It's a 4 kilo-ohm per centimeter square. And then we also will move on to a fabricate high power devices. So the next topic that I'm going to talk about is this conventional 3,5 gallium arsenide indium phosphide on silicon, and involving the band structure engineering, and then how do you use this technology to put active devices on silicon. And everybody knows in the silicon photonics integrated circuit and laser is the elusive components, and people have been working on this for the past 10 years or so. And we have made this laser arrays, we make microdisc lasers, and we also do this integrated ring laser with the photodetectors and so on. So I'm going to talk about a little bit of this detail in this technology. As you integrate 3,5 material devices on silicon, you can do die-to-wafer bonding, you can do direct epitaxy, you can do wafer-to-wafer bonding, and people have been working on these different technology, different approaches for quite a long time. And of course, every technology has its pros and cons, and then our focus have been on this direct epitaxy. So that's why I like to call this technology is epi for epi. It's doing epitaxy for the electronic and photonic integration. These are the defects that you have to solve this problem, and these are the problems and people are facing with these different technologies. And so when you do the heteroepitaxy, you're going to deal with the threading dislocation, you're going to deal with the anti-phase boundary, and you got to deal with the stacking fault. And we have seen all this, and you can find the detail in our review paper a few years ago. And one technology that we chose that we think is very promising is called aspect ratio trapping. And this is involve selective area growth. And you can do selective epi, or you can use it to create some template. And the idea is if you make this trenches small enough, and then because of the aspect ratio, the height and the bottom, and then the defect generated at the heteroepitaxy will be confined at the interface. And then at the top of it, and it will be much cleaner, and then you can put active devices on it. And we have used this technology for the past 10 years or so, and we find that it is very effective. It's a temporary technology. We make microdisc lasers, micro ring laser, fabric Perot lasers, and then with this V groove that we created, and on the 001 silicon, and you can get rid of all the interface boundaries. And then the defect, it can be as low as mid 10 to the 6, the strand dislocation density, and this interface domain free or interface boundary free. And so we reported this back in 2015. And then we have these lasers and electrically pumped lasers, and that have been demonstrated on these template, and the micro disc lasers and micro ring lasers, and these have gone on the cover of Optiker, and we have reported this since 2016. And these are a very small, and the outer ring size is 3 micron. And we find that this FSR and also is very close to what they're supposed to be. And we have also grown 1.5 micron lasers and on silicon and with the MOCVD. And this is the one with the indium phosphide on the V groove or planar silicon. And then we have to go through some 3 micron of buffer layer. And then we demonstrate this room temperature lacing of the 1.5 micron, the quantum dot lasers that is grown on it. And also we report this in the past couple years. And they are single mode lacing at in the 1.5 micron band. And the threshold is around 1.3, and I think the lowest was 1.1 kilograms per centimeter square. And then we think that, well, using the thick buffer is still difficult. So we look into this selective area epitaxy, and we hope that we can eliminate this thick buffer by confining the defect in the bottom. So this is what we try to do. We try to eliminate this 3 to 4 micron buffer layers. And then with this, we can make lasers, and that is the active region, and without a thick buffer layer. So this is, again, use the aspect ratio trapping, and we can trap the defect in the bottom. And we first try to do it on silicon and then on SOI. And after that, then we turn this concept sideways. And then we think, well, if we do this aspect ratio trapping, and we keep growing on the lateral direction, and then the defect is confined at this interface here, and then you can grow as long as you want, and then you can have a very large area. Indium phosphide is sitting right on the box and the burial outside, so that will be wonderful. And so this we call it the lateral arc. And this, so we have demonstrated this, we call the bufferless 3.5 laser, and then it can be integrated with the silicon waveguides easily. And so we demonstrate this, and also at the same time, there are a couple other groups that are also working on it as IMAT, and they demonstrate getting arsenide-based laser in a 1 micron range, and also IBM Zui, and they also demonstrated gallium arsenide-based lasers and micro lasers and 850 nanometer range. And then we demonstrate our lasers in the telecom band, 1.3 and 1.5 micron. So this is, again, this is the concept. This is conventional aspect ratio trapping. And with this, you can find your defect in the bottom, and this is defect free. And then with the lateral arc, then you can find your defect in this region here. And then you can grow out of this trench. And this is what we try at the beginning. And these are the nano-rich and selectively grown on the 001 silicon using the vertical arc. And we can, like, then we insert indium gallium arsenide quantum well into this indium phosphide. And then you can see that the defect that the gallium arsenide, we go through a very thin layer of gallium arsenide and then go to indium phosphide. And later on, we find that we don't really need this thin layer of gallium arsenide. And we have made the 1.55 micron band nano lasers, and with the Fabry-Perot cavity, and on the SOI using this concept. And this Fabry-Perot cavity that we are talking about, it's not the conventional like 1 millimeter size. It's in the micron size. And these are the 20 micron, 30 micron, and some of the short ones are 12 micron. And these are the lasers, the nano laser arrays that you can pattern. You can use photolithography and pattern on the buried oxide, and then grow the indium phosphide and then the active region. And then this is the end facet. Then you can cut the end facet with FIB. And we get this 1.5 micron band nano laser lasing. And these are the cavity length is 60 micron. And then we find this, the optically pumped is down to like a few tens of microjoule per centimeter square. And one thing very interesting that we find, it depends on the cavity length. And you can actually tune the lasing wavelength. This is with the same quantum well that we grew that can cover from 1.3 micron to 1.55 micron. And we have reported this a couple years ago. And so this is, it would depend on the length of the cavity, and you can check it out. And then we move on to using the combination of the vertical and the lateral arc, and to make this lasers. And one problem is because the thickness, you need the aspect ratio and to confine the defect. And then that will, you are controlled, limited by the thickness of the silicon on top on the SOI. So we have to do a combining this lateral arc and then add it with the vertical growth and to get this defect free. And then lasers, and we managed to do that. And then we find this very low threshold, the 16 microjoule per centimeter, that's lasing. And then later on that we find that we really want to increase the size of this lateral arc concept so that we can get a larger area indium phosphide on the SOI to work with. So this is the continuous indium phosphide epi that we found that it can grow laterally and in this direction. And then we find that the defect is trapped, and the defect is trapped at the interface, and this is at the interface. So the lateral arc can grow continuously and in the lateral direction. So this is the concept that we do the undercut, the etching, and then now we try to increase the size from a few micron, first half a micron, and to 7 micron. And then with this, and then we try to be able to have the flexible indium phosphide dimension, and so that we can integrate it with the waveguides and so on. So this is the cartoon of how we create this pattern, and this is silicon patterning, and then the oxide encapsulate, and then we do the undercut, and then they do the selective epi, and to fill this gap, the lateral arc, and then we can remove the oxide, and then you can have a silicon template. And so this we can create the length of this. It can be a submicron wire, and it can be a very long, large dimension. So you can make it a square, like a 7 micron by 7 micron, or you can make it 7 micron by a few millimeter. And so we have demonstrated this technology. And again, this is the patterning technology. And we create this large dimension, and we call it the membranes. And the previous ones is you can make it small, and then you can call it a submicron wires. And so this is the SEM that is shown on the 500 nanometer pattern, 1 micron pattern. And then in this direction, we grew it up to 7 micron. And these are the in-plane indium phosphide on insulator. And so for the larger dimensions, we make it 5 micron, we make 10 micron. And these we call it this indium phosphide membranes that we can make a larger size laser with. So these are the sub-wavelength laser arrays that we have fabricated, and these are sub-wavelength arrays that we find that as a lasing, and these are the pure indium phosphide. So it's a lasing around the 900 nanometer range, and it's optically pumped. And then this another one, and I'm trying to show you, it is 3.5, the photodetectors on this same indium phosphide on SOI platform. And we also fabricated by growing N-type and P-type, and in the middle we grew this insulating indium gallium arsenide. So this is a lateral photodetector that we make, and then we can put metal on both sides. And then with this small lateral photodetectors that we fabricated, and we were able to have a very dark dark current and very high photocurrent and very low dark current. And you can see the dark current and both in the 1.3, 1.55 nanometer, it's a very low, and then the photocurrent is quite high. And this is very high speed, and we tested in the high speed the 3 dB bandwidth, and we find this pulse is only 10 picosecond. And if you do the Fourier transform, and you will get up to 44 gigahertz. And these are the 2 micron length photodetectors. And we also test this, the eye diagram testing, and we find that it has a very clear open eye at 40 gigabit or 40 gigahertz. So this is all I have, and I want to show you that these are the work of my group over the years, and for many years. And these are the students that I want to acknowledge their hard work. And the work is sponsored by the Research Grants Council and Hong Kong Innovation Technology Fund. Thank you. Thank you for your attention.